Hello everyone. So in the last module, it got cut off abruptly because I was reaching the maximum time that I can record. And I just wanted to finish off what I was going to say about our plots. Now, we went over the radial plot, we went over the dot plot, contour plot, and our radial probability distribution plot. And one thing students ask is, if we have a node here, if we have a node here and a node here, how is it that an electron can pass from here to here if there's no electrons there? Well, that is related to what we've already learned about. It's the Heisenberg uncertainty principle. So if we know where an electron is, we can't know how fast it's moving. So quantum mechanics pretty much says we can't ask this question. So if we know our probability distribution, we can't know how it moves around. And that's just something that we have to take in. And there are actually whole courses, graduate courses on this subject. So that's something else. That's something that you learn about later if your career path takes you that way. But for our class, what is our purpose? What should we know? Well, what we should know is I want you to know what the plots look like. So I want you to know what our plots look like, know what a node is, where to find the node in a plot, know the shape. So here, the contour shape, it was a piece of the ball or a wedge of the ball. So we know that an s orbital would be spherical. And have an understanding of the distance of that electron, right? So the most probable position of that electron from the nucleus, we talked about that before. So it would be here for this radial distribution here, or the radial probability, that probability, and that probability. Okay, so these are what's going to be important for our class. Okay, so those are the 4 different types of plots. Again, all from solving the Schrodinger equation. Now here, I just have some examples of the probability, different kinds of dot plots, so that way you can just see what those look like. And they're just, so here we have the dots, it's more dense in the center, so we're going to find the electron most likely there. Here's in the 1s, here's in the 2s, and we can see that there's one node in the 2s, and if we go to the 3s, we see the 2 nodes. And then here are our contour plots. So this is the contour probability. And then here is a plot where we just put all of the probability distributions on the same graph. Notice that's our psi squared times our volume, and that's why they all start at 0 over here. Okay, and the reason I show this is we're going to come back to this in the next chapter again. We'll be talking about that. Okay, so just a different perspective. And then the likelihood of finding the electron here, and then here, and then here. So it should make sense. Okay, so we have already talked about the quantum numbers, but for each electron, I'm gonna repeat this. There's gonna be a set of 4 numbers that describe the energy of those, and it'll describe the location as well. And these again are called quantum numbers. Okay, and to kind of this is pretty abstract. So I put this picture in here to kind of get a big picture of what's going on. So over here we have what's called a principal quantum number. So that's kind of the big portion here, and you guys probably understood it before when they called them their shells. Okay, so this is going to be our n's. So this is going to be our n. That didn't mean to look like it's supposed to be a comma, but here's our n. And n are going to be our counting numbers, like 1, 2, and 3, and so on. So you have this shell, or principal quantum number, that houses, and then we describe next the angular momentum. So what that will describe, well, it doesn't house angular momentum, but here I want to talk about the angular momentum first. That's represented by our L. We saw that in the last module. And this represents the shape. And the shape of what? Our orbitals. So the L will represent our shape. And here we have our S, which is the spherical, and then the P. So our S's and P's, and notice, and we haven't talked too much about the P's yet, but I know you've seen them, and these are our dumbbells. We'll talk about them in a little bit. And then within our shells, we have the sub-levels, but then we have our orbitals. And our orbitals are going to be represented by how many orbitals we have, and that's going to be our m sub l's, and that is our magnetic quantum number. So here we have our shell. Within our shell we have our sublevels, our 2s, and then we have our sublevels of our 2p. And then we have our orbitals within those sublevels or subshells. Lots of different terminology, so I'm going to try to use all the terms that you guys learned before. Let's go to our orbitals first. So our orbitals, again, the shapes, they're determined by our angular momentum L. So the s orbital looks like a sphere. We've talked about that. The p orbital is a dumbbell. Our d's, we're going to go into this in a little bit more detail in a little bit, but notice that it's a pair of dumbbells together, and then our f orbitals, where we have more than one set of dumbbells. So we've got our sphere, we got our p orbital, d orbital, and f orbital, and those are represented by 0, 1, 2, and 3. So again, S, P, D, and F. And we've talked about nodes before, but let's just review again. It's the region where the electron density is 0. And if you know where the electron can't be, we know that we can combine it to a restricted space and volume, but there's a formula that you can use as well. The total number of nodes is n minus 1. So here is an example for a 2s. If you have n equals 2, L equals 0, you just take the n, which is the 2 minus 1, that equals 1. So you know that in a 2s, you would have one node. Okay, and we saw that in those plots, and in the diagram, and the contour plots as well. So let's go back to our s orbitals. There's a few more things I'd like to point out. So here is a contour plot again, and we know that the shape is spherical. We've already went over the radial distribution function. And here is the maximum distance over here, and we actually give you a value here, 52.9 picometers. But what I wanted to point out here again is what happens as n increases. So as our n increases in this direction, we know that the orbitals become larger and that they contain more nodes. Okay, so just going over that again, they become larger and they contain more nodes. Okay, so that's, again, refreshing our memory on S's. But now let's go to P's. We haven't talked about P's so much. Now with P orbitals, we've already talked about its angular momentum being 1 and assigning that. But to refresh your memory, there are 3 P orbitals. We have 3 P orbitals. And here they're plotted on the X, Y, and Z axis. So you can look at this like the dumbbell shape being skewered on that axis. So here we have the dot plot on the axis, and here they're just showing you what these look like, and these are called lobes. Now we have 3 orbitals, and each are going to be on a different, or each is skewered by a different axis. So this is our px orbital because it's on our x-axis. This is the py orbital because it's skewered on the y-axis, and this is our z orbital, pz orbital, because it's skewered on the z-axis. And what I want to point out as well is that the node is located at the nucleus. Okay, so the nodal plane is right here where we're not going to find any electrons. Now, each orientation, we've talked about the m sub l a little bit, and I'll talk about it more when we go over quantum numbers, but I want us to get used to this. What does m sub l mean? That's our magnetic quantum number. And here, it's the orientation of each. So a px would be -1, a py would be 0, and a pz could be +1. Okay, so 3 orientations. And if you recall in the video when we talked about m sub l, to find m sub l, you go minus l through 0 to a plus l, and that's what we do here. So if you know l is 1, you just start counting minus 1, 0, and 1. And that's how you figure out all of your m sub l's. And that should, then you match it up. P has 3 orbitals, should have 3 orientations. Okay, and here is the radial distribution function. So this looks a lot like our S radial, our 1s distribution function, doesn't it? But here is our 2p. So notice here we have the 0 again, 0 volume. And our most probable distance is over here. Now, if we look at our wave function for a p, we know that we're going to have n equals 2. L should be 1. And our m sub l can be all of these numbers, 1, negative 1, 0, and plus 1. But instead of writing all that, we just say psi 2p, and that's all of our wave functions. And here you can see all of the orbitals plotted on one set of axes. So that's what all of the 3 orbitals looks like. Okay, so those are our p orbitals. Let's go on to d. And I know a lot of you have seen d. Now d is a refresher. We have 5 d orbitals. The L is going to be 2, so I want to refresh everyone's memory on the L's again. So our L, if our L is 0, 1, 2, 3, 0 is S, 1 is P, 2 is D, 3 will be F, so we're focusing on the D's. Now we have 5 different orbitals for our D and they're aligned on different planes. And we use this notation, dxy, dyz. It depends on how they're oriented. So the m sub l start with L, minus L, go through 0, and go through a plus L. So we have minus 2, minus 1, 0, plus 1, and plus 2. And these represent these 5 different orientations. Now here, this is the dyz orbital, and so they show you the contour, or so the dot plot here, and then we have a contour plot here. And they're trying to show you that this is going to be on the y and z plane. So kind of the way to draw it is they do this box and line it up with the y and the z. The dxy orbital, so they have it here on this plane, so they're trying to draw it like that. So this is the dxy, and then the dxz, same idea. Then you have the dx squared minus y squared. And then over here is the dz squared orbital. Notice it kind of looks like a pacifier in a way, and it has like a little ring in the middle. And again, the dot plot there. And and really for our class, I'm not going to make you draw these. Especially because we're online now, but you should know that there are 5 different orientations and we have 5 different orbitals. And this is what it looks like when they are all plotted on the same axis. So it's getting pretty busy here. And finally, let's go to our f orbitals. So the L is 3, so if we do the L again, 0, 1, 2, 3, this is going to be S, this is P, this is D, that's F. So F, we're going to focus on the L equals 3. Now the F, if you recall, has 7 orbitals. So if we start at our m sub l, so it would be minus 3, minus 2, minus 1, 0, 1, 2, and 3. So 1, 2, 3, 4, 5, 6, 7. And here are our 7 orientations. And notice with Fs, we don't, they get more complicated. And in our class, we don't talk about these so much. So what are you responsible for? You have to know how to find the m sub l's, you have to know what your L is, and you have to know that there are 7 orbitals, 7 different orientations. And this leads us to when all of the atoms overall are all plotted, here we see that atoms are spherical. Okay, so the big message after all of this is that this is, through quantum mechanics, we find that it's proof that atoms are spherical. Okay, so I'm going to end this module because we're running out of time, and I will begin again on the next module.